Hello, myself Usman Kazi.
And I'm Disha Kante.
Our project is Cricket Points Table Management System. The main idea behind our project is to automate how cricket tournament points table is updated and maintained. Normally, this is done manually after every match. Someone has to calculate the points, wins, and losses, and then rewrite the table. We want to make the whole process automatic using a data structure.
In our system, we've used three main data structures: a hash map, a queue, and a stack. The hash map stores all the teams and their stats, like matches played, wins, losses, and points. Uh, the queue is used to store the match results in the order that they are played and then process them one by one. And the stack is used to record suspicious activities. For example, if a team suddenly starts losing badly or repeatedly, that gets pushed onto the stack so we can review it later.
Now talk about the code. We have a team structure that hold the team name, number of matches, win, lose, and points. Then we have the match structure which keeps track of two teams and their score.
For suspicious events, we have a suspicious structure, which helps us form a stack of such incidents. We also have a hash map, which is basically an array of linked lists, where each index stores the teams whose names hash to that value. The hash func creates a unique index for every team name. Whenever a match result comes in, the program checks the hash map. If a team does not exist, it creates one using create team, and if it already exists, it simply updates that team's record.
When we enter the match results, they first added the queue using NQ matches. The queue follows the first in first out order, so matches are processed in the exact sequence they were played. Once we choose the when we choose when we Once we choose to process them, the process use process matches. The function dequeue one match at a time, check who won and who lost, and update both team details inside the hash map.
Inside that function, if a team loses by more than 100 runs, or if it has already lost 3 or more matches, the program considers that suspicious. It then pushes that event onto the stack using push suspicious. The stack follows the last in first out order so that the most recent suspicious event is always on top and easiest to review.
After the matches are processed, we can display the points table. The display points table function collects all the teams from the hash map, sorts them by points, and then print them in a nice tabular format showing a matches, wins, loss, and points.
Finally, the menu function provides a simple interface for the user. We can choose to add match results, process all matches, display the points table, show suspicious events, or exit the program. Now I'll run the program. Thank you. So, do you have any questions?
Yeah, so very first thing, what's the main goal of your project?
The main goal of our project is to automate the cricket tournament points table so that all match results, team stats, and suspicious patterns are managed automatically using data structures.
Okay.
Also, which data structures did you use and what's their role?
I use three main data structures. First, hash mapping. Hash mapping is used to store updates and each team detail quickly. Second, I use queues to store and process match results in order they occur, like first in, first out. And second, I use tags to record a suspicious event for review, like last in, first out. The structure provides fast, accurate order processing and efficient data management.
Okay. And well, why did you prefer a hash map instead of array of lists?
Because a hash map gives constant time access O1 on average. So even if we have a lot of teams, we can update or search for a team instantly without scanning the entire list like we'd have to do in arrays.
How does the queue fit into the system?
The queue is temporary store match result before processing. Each match result is in queue as soon as it's entered and dequeue when proceed. This ensures matches are processed in same order they are played.
And what's the purpose of using a stack here?
The stack keeps track of suspicious team performances like repeated heavy losses. Since stack works in last in first out order, the most recent suspicious cases are always reviewed first.
How do you make sure that there are no duplicate teams?
Before inserting a new team, the system checks if a team name is already exists in HashMap. If it does, the new entry is ignored or flagged, ensuring each team is unique in the table.
And what exactly happens when a match result is processed?
When a match is processed, it's taken out from the queue. The winning and losing team stats are updated in the hash map. And if the loss margin or performance looks suspicious, it's pushed onto the suspicious stack.
How do these data structures work together?
These data structures work together, like hash mapping is used for fast data retrieval and updates, queues is used for maintaining a match order, and stack is used to track a suspicious activities. Together they prove a powerful and efficient system for match and point management.
And like, what advantages does your system have over manual management?
It saves time, removes calculation errors, and updates everything instantly. Plus, it can easily handle large tournaments and give automatic performance insights.
What's the final conclusion of your project?
The conclusion of our projects is that the cricket points table management system efficient use data structure to manage tournament data automatically.
Well, that's it from my side. Thank you.
Good morning, everyone. Today we'll be presenting our project Car Parking Management System, created by myself, Kevin De Silva, and my teammate Hardik Erat.
So let's begin with the problem statement. In large parking spaces, it becomes very difficult to manage vehicle entries uh, and track which slot is occupied and ensure that empty zones are reused efficiently. So our objective was to automate this entire process and make parking faster, smarter, and less error prone. We wanted the system to automatically assign unique tags and parking zones to vehicles on check-in and prevent duplicate entries, reuse vacant zones efficiently, and provide instant access to information like occupancy, vehicle location, and entry order.
To implement these features, we used a combination of efficient data structures. The key idea was to use the right structure for each operation, ensuring both speed and clarity. Here's how each structure plays a role in the system. Map. Used for zone to tag mapping. This keeps all zones automatically sorted by zone number, which helps when generating organized zone summaries. An unordered map or hash map. It's used for tag to zone mapping. It provides constant time for searching, inserting, and deleting entries. So, if we want to quickly find where a vehicle is parked, the structure gives an instant answer. List. It's used to store vehicles in their arrival order. This allows us to display the parking log from oldest arrivals to the most recent arrivals. Stack. Used to store available or vacant zones. Since it follows the LIFO principle, the most recently vacated slot is reused first, ensuring that space is utilized efficiently.
So now looking at the architecture, we see that how all these structures work together. The system has three major operations, which is vehicle check-in, vehicle checkout, and query operations. Vehicle check-in, so when a new vehicle arrives, the system first checks if the tag already exists, and if not, it assigns the next available zone, either a new one or the one that was freed earlier, and updates all the data structures. Vehicle checkout, when a car leaves, the system removes its details from all the data structures and adds the zone number back to the stack of vacant slots. And talking about query operations, the user can search by a tag or by zone. For example, we can instantly find where a vehicle is parked or check which vehicle occupies a specific zone. There are also reporting features like the arrival log, which shows vehicle by check-in order, and the zone summary, which displays all the occupied zones sorted numerically.
Here we list some of the key functions implemented in our code. Place Auto handles the vehicle check-in process. Retrieve Auto manages the checkout process and updates data structures. Functions for query by tag and query by zone allow fast lookups. Show arrival log and show zone summary help display reports in an organized format. These functions together ensure smooth operation and efficient management of the parking system.
Talking about advantages, our system has several key advantages like efficient space utilization since vacant zones are reused immediately, fast operations thanks to hash maps for constant time lookups, and organized reporting using lists and maps. And it's scalable, meaning meaning it can easily handle larger parking slots without major changes to the code.
To conclude, our car parking management system demonstrates how powerful data structures like maps, lists, stacks, and hash maps can be applied to solve real world problems. The result is a system that's efficient, organized, and scalable. In the future, this project can be extended with features such as automated pricing, time based billing, or even license plate scanning for smart entry. Thank you for listening. Now, coming to the main class, Automated Lot. This class contains all the logic and data members needed for our system. Let me quickly go through the data structures used. An unordered map called tag to zone map used to quickly find which zone a particular vehicle is in. Lookup here is in constant time O1. A map called zone to tag map. This stores zone numbers as key and vehicle tags as values, keeping them automatically stored by zone. A list called vehicle sequence. This maintains the exact order of vehicle arrivals, like a parking lot. A stack called available zones. This keeps track of freed up zones so they can be reused when a new vehicle arrives. And finally, an integer next available zone that keeps assigning new zone numbers if none are free.
Now, talking about the core functions, the very first thing is place auto. So when a new vehicle comes in, this function checks whether the tag already exists to prevent duplicates. If it's a new vehicle, it assigns the lowest available zone either from the stack or the next new number and records it in all maps and prints a success message.
The next function is retrieve auto. This handles the vehicle checkout process. The system searches for the vehicle in reverse order, latest to oldest, using a reverse iterator. Once found, it removes it from all records. pushes its zone back into the available zone stack for reuse, and confirms retrieval.
Now, the next functions are query tag and query zone. So these are quick lookup functions in which query tag tells us which zone a vehicle tag is currently parked in, and query zone is a function which tells us whether a specific zone is occupied or empty.
Next is display arrival list. This shows all vehicles currently parked, ordered by the time of arrival, the latest first, and generates zone summary. This gives a complete summary of the lot, which zone has which tags sorted by the zone number.
Talking about print console menu, this is just a simple function that prints the menu again and again so that the user can choose from these options.
Obtain int input is just for obtaining the option which we have to choose. And
And
well,
similar thing with the obtain string input
yeah.
too. So now talking about the main function, it's just a simple menu-driven program that repeatedly asks the user to choose an option, from placing a new vehicle, retrieving one, displaying the parking log, checking summaries, or shutting down the system. And this program continues to display and go on like until the user selects the system shutdown option.
In summary, this project demonstrates how C++ can be used to model a real-world automation system efficiently. It combines object-oriented programming, STL containers, and interactive console input to create a smooth logical parking management flow. It's a great example how data structures like maps, lists, and stacks can work together to solve practical problems in an elegant way. Now I'll run the code. Hmm. Thank you.
Thank you.
So, do you all have any questions?
Yes. Why did you use an unordered map instead of an array or a list?
Because an unordered map allows O1 average time insertion, deletion, and search using hashing. Arrays or list would require linear search, which is slower, especially as the number of vehicles increases.
So my question is, what is the role of stacks in your system?
So basically, the stack stores the availability of the zone numbers, which is the empty zone numbers. So whenever a car leaves, its zone number is pushed into the stack, and when a new car arrives, the top zone number is reused. So this ensures that the most recently freed slot is filled first, which is basically the LIFO principle.
How does your system prevent duplicate vehicle entries?
Before parking a new vehicle, The program checks if the tag already exists in the unordered map. If it does, it displays an error message and doesn't assign a new zone.
What happens when a vehicle is retrieved?
So whenever a vehicle is retrieved, it's searched in the unordered map, and its zone number is freed and pushed into the stack. Then the vehicle is removed from the list and maps, and then at the very end, a success message is displayed, confirming the retrieval of the vehicle.
Okay. And why did you use a map for zone to tag mapping instead of an ordered map here?
I used a map because it stores data in sorted order by zone number. So when I display the zone summary, it automatically lists the zones in ascending order. No manual sorting is needed.
What happens if user enter a wrong input like a string instead of an integer?
In that case, the program checks for input errors using the cin.fail thing, and inside the which is inside the obtain int input function. And if invalid input is detected, it clears the input buffer and prompts the user again, so the system doesn't crash.
How do you ensure data consistency between all the structures that you've used?
Every operation updates all relevant structures together. For example, when parking a car, both unordered map and map are updated. And when removing it, both are cleared along with the list entry. This keeps all parts of the system synchronized.
What is the biggest challenge you faced while developing this?
Well, the main challenge was managing multiple data structures together while keeping the data consistent during insertion and deletion, and especially ensuring that when a car leaves, all three structures like the list, map, and stack are updated properly.
What are the advantages of your system compared to manual parking?
The advantages are that it reduces human error, it tracks vehicles automatically and provides real time status of slots. It reuses empty zones efficiently and can easily be scaled or integrated with sensors or billing.
What is your overall conclusion of your project?
Well, this project shows how fundamental data structures can be combined to solve real-world problems efficiently, and it demonstrates good system design, modularity, and data management, making it a reliable and scalable parking solution.
That's it.
Thank you.
Thank you.
Thank you.
Thank you.